Hello, everyone. My name is Hamza Butt. I am a PhD candidate from Virginia Tech. Today, I will be talking about pressure gradient effects on boundary layer superstructures. When any fluid moves over an obstruction, like a flat plate, a very small region of momentum deficit is formed due to the presence of wall shear. This is called the boundary layer. Most of us can relate this to the presence of the no-slip boundary condition that occurs at the fluid structure interface. In response to this, turbulent flows also induce pressure fluctuations in that surface. These are often noted in the form of radiated sound or surface vibrations. Most of us have experienced this phenomenon in the form of cabin noise in cars and other vessels. The understanding of this phenomenon carries great importance for commercial and defense industries. These pressure fluctuations can be characterized into their wave number and frequency components with the help of the wave number frequency spectrum. While there's a lot to unpack here, we will look at just the important bits for now. The brightly colored contours dominate the spectrum. This region contains the influence of the convective structures, which is evident by the slope of this ridge in the streamwise wave number direction. This is called the convective ridge. While the convective ridge is the most dominant, the most interesting bit for us is the subconvective region, as it contains the information about the low wave number sources of wall pressure fluctuations. This region contains the effects of the sources that are either large or appear to be large, and or quick or appear to be quick. To understand the sources of the wall pressure fluctuations and unveil the large structures in the boundary layer, experiments were conducted at the Stability Wind Tunnel in Virginia Tech. This is a closed-circuit subsonic wind tunnel, which has a modular test section with a cross-section of 1.85 by 1.85 meters. This is a schematic of the test section. The two hard walls are shown on either side using black solid lines. Boundary layer was tripped over the port side of the wall using a trip strip, which was mounted about 3.5 meters upstream of the global origin. Velocity measurements were taken at about 2.7 meters from the origin in the downstream direction. A NACA 0012 was mounted in the middle of the test section, and the change in its angle of attack caused the pressure gradients on the port wall to vary. A picture of an experimental condition is shown in this slide. The port side is on the right-hand side, while the starboard side is on the left-hand side. The NACA 0012 is mounted in the middle. The change of the angle of attack of this airfoil varied the pressure gradients in the measurement location. The modular thickness increased as we moved from the -10, which is pitching towards the measurement plane, to 12 degrees, which is pitching away from the measurement location. The average height of this upper edge of the measurement plane is shown with the boundary layer profile in SI units on the left-hand side and in the wall units on the right-hand side of the figure. The -10 degree case within our measurement plane corresponds to the favorable pressure gradient. The 0 degree case shown in black corresponds to the small pressure gradient, and the 12 degree case shown in red is the adverse pressure gradient. The color codes will remain consistent throughout this presentation. The plot on the right confirms that we are in the lower portion of the boundary layer's log region, which is important for our study. Planar time-resolved PIV measurements were acquired using two high-speed cameras placed about 2 meters across from the measurement location on the starboard wall of the wind tunnel. These cameras used 200mm lenses each and sampled the flow at roughly about 3.5 kilohertz. The individual field of view were acquired, cropped to size, and stitched together using a hyperbolic tangent function shown here. Once the measurement was stitched together, this slide shows the convection of these large structures downstream for the favorable pressure gradient case, which is shown with the blue lines. In this video, we can see that the structures appear to be tensioned and packed closely to one another as they convect downstream. They're slender and elongated in the streamwise direction, and they're separated from one another by these smaller but faster moving structures. It is important to note that the faster moving structures are also on the order of about 2 to 3 boundary layer thicknesses. The separation width of these large structures was quantified using spatial correlations, and for the favorable pressure gradient was found to be about 29.4 millimeters. On the other hand, the adverse pressure gradient case was taken for the 12-degree angle of attack of the airfoil. Structure appear relaxed and distant from one another, and they appear thicker as compared to the favorable pressure gradient case, which is confirmed by the spatial correlation. The correlation width, which quantifies how the structures are separated from one another, is about twice as much as we saw for the favorable pressure gradient case. To understand this in detail, anchored correlation coefficients of the streamwise velocity are plotted in this figure. The contours are cut off at a specific level to show comparison. A high correlation is seen around the anchor point, which drops as you move away in any direction. This drop is stark in the streamwise direction, while the flow remains correlated till the edges in the streamwise direction for a longer distance. This indicates streamwise biased flow anisotropy. As we move towards the adverse pressure gradient, this correlation region increases in both directions. As we can see that for 0-degree cases, it starts to get elongated in the streamwise direction and gets much larger for the adverse pressure gradient case right here. However, upon normalizing with the boundary layer parameters, a nice collapse is observed for these contours, indicating a dependence on the outer boundary layer parameters. Once the turbulence statistics of the flow was discussed, we have plotted a narrow slice of the wave number frequency spectrum for comparison between the velocity fluctuations and the wall pressure fluctuations. First of all, while the acoustic line is plotted for both figures, it remains rather uninteresting and uneventful for the velocity spectrum. However, the pressure array separates the acoustic sources into a region that is bounded by the acoustic line. Nevertheless, the dominant convective ridge is also visible, shown here as black dashed lines. While the convective ridge is distributed about this line, the pressure plots, the convective ridge of the velocity shows a different slope. This could be because pressure is a global parameter and incorporates the effects of the entire boundary layer, including both the slow inner and the fast outer layer. On the other hand, velocity is measured in just one plane of the boundary layer at a specific height. I would also like to point out that the different ranges of these wave numbers for both velocity and pressure spectra are because of the different sampling rates and the different temporal and spatial resolutions provided by the both modes of measurements. Both spectra show higher levels at the subconvective regime as compared to the superconvective regime, indicating a connection between the large-scale fast-moving flow sources and the low wave number pressure fluctuations. It is important to recall that these measurements were not acquired synchronously, and hence a discussion on direct correlation, or if you might call it causation, warrants further synchronous investigation. Therefore, at this point, we will just like to comment on the correlation between the low wave number pressure fluctuations and their sources in the velocity spectra. With that, I would like to draw the following conclusions from my presentation. Streamwise oriented structures as large as 1 to 20 boundary layer thicknesses exist in the lower log region of the turbulent boundary layer. They meander in spanwise direction as they convect downstream. Their length scales are boundary layer dependent and are biased towards the streamwise direction, showing flow anisotropy. The wave number frequency spectra of the velocity fluctuation reveals the dominance of the low wave number sources at moderate to high frequencies. The spectral level for pressure and velocity occur at similar wave number regions, indicating correlation. However, the pressure velocity measurements must be conducted synchronously to reveal direct connections between the sources of the pressure fluctuations. With this statement of acknowledgement, I would like to thank you for your attention.